right, now we're going to look at the problem of unstable systems. So here's an example of a system that is unstable. So we have this airplane coming in over here. He's coming in for a landing, and seems to be having a little bit of trouble here. We zoom in and we see, oh, that's not good. Boom. So here it is from a different angle. It's coming in. It does a little roll. Yeah, this is the kind of rolling that airplanes aren't really designed to do very well. So, unstable system. So the paper, Respect the Unstable, goes through and makes these are the three main points. Basic facts about unstable plants. First of all, unstable plants are fundamentally and quantifiably more difficult to control than stable ones. Second of all, controllers for unstable systems then must be operationally critical. And third, closed-loop systems with unstable components are only locally stable. And so the conclusion drawn is an unstable system is a dangerous system and needs to be treated with great care. So we've looked at the sensitivity function, which is again the transfer function from R to E. We have the sensitivity function. In general, for good tracking, we desire E to be small over the same frequency range as R, so basically low frequency. So that is, we want the sensitivity function to be small at low frequencies. So in fact, if you have it 0 at DC, then you can track a constant input with 0 steady state error. So this is an important problem in looking at the sensitivity function of this setup. So we have that situation. So now we're going to go through and look at quantifying the control difficulty using Bode integrals. So for a stable plant, the Bode integral says this. If I take the sensitivity transfer function evaluated at j omega, take the magnitude of that and the natural log of that, and integrate that quantity over from 0 to infinity, I will get 0. That integral is 0. So notice that in order for the integral of a function that's not 0 to be 0, that means I have some parts that are negative and some parts that are positive. And the area under the curve must be, area under this part must be the same as this. So why do we draw the curve like this? Well, remember our sensitivity function, in order to track signals like constant signals, I need a small sensitivity at low frequency. So I need this to be small in order to have good tracking. So what the Bode integral is saying is, if I'm going to have a small part, that is, so if you think in terms of what log absolute value is saying. So if the magnitude is equal to 1, the log of that is 0. Right? The natural log of 1 is 0. Actually, any log of 1 is 0, even log base 10, whatever. They're all defined so that log of 1 is equal to 0. So if I look at the natural log of this quantity, so this is 0 here in this scale, in this vertical scale, is basically correspond to magnitude 1. And so what this is saying is, if I have magnitude less than 1, I'm also going to have magnitude greater than 1 occurring. And in fact, the area under these two must be identical. Okay? Equal areas. So in particular, what that's saying is, this part must be here. That is, I can't ignore the fact that I'm going to have, so if, for example, I had a reference signal that had frequency content in this area, it's not going to track very well. Okay? The sensitivity is going to mess us up in terms of tracking. So, but we cannot get rid of this. So it would be nice, ideally, if the error So remember, the sensitivity is the transfer function from the reference to the error. The error is being the difference between the input and the output. And it basically is an estimate of how well the system is tracking the input. So what this is saying is I can track it good at low frequencies. It does not track it well at all for higher frequencies in these areas. So we have that. So in particular, what we cannot do is we cannot make this part small without making this part large. Okay, we can't make this part small without making this part large. So this is what we have when we have a stable plant. We have these two must have equal areas. When we have an unstable plant, Bode integral says this. Instead of this integral being equal to 0, we actually have it equal to this, which is equal to pi times the sum of the real parts of the poles in the open right half plane, in the closed right half plane. That's what this is saying. So if I have poles that are far in the if I have poles that are far in the closed right half plane, that's going to give me a bigger number here. So what is this saying then? This is saying that the area down here is less than the area over here. That is, this is a positive quantity, which means I'm going to have more area above the 0 line than I will have below. Okay, so this part is now larger than this part, is what this is saying. And what this proves is that systems are unstable systems are quantifiably more difficult to control. So instead of having 0 here, I have something positive, and that means that there's a shift between these two areas. That makes it quantifiably more difficult. And the more unstable, that is, the further into the right half plane the poles are, the larger this quantity is, the larger this is. And so again, I could still have a low value here, but that means I'm going to have large values over here. So the author calls this digging dirt. Okay, and basically, so if I get rid of some over here, I have to put it over here. That's the basic idea behind the Bode integral. So the author makes the point that the unstable system is quantifiably more difficult to control. The author of the Respect the Unstable paper draws the point of available bandwidth. Available bandwidth for a system. So here is an example control loop that involves a digital controller. So notice I have this in the Q domain. The digital controller has digital to analog converters, analog to digital converters. There may be saturation in our control signal. So for example, the digital to analog converter has voltage limits, right? It has when you have a digital to analog converter, it has limits. And so if this signal tries to become greater than what these limits are, that basically corresponds to having a nonlinear saturation in the system. Similarly, the analog to digital converter can also have limits associated with it. So I have a saturation associated with the system. The plant, then, itself, generally speaking, a lot of systems that we would want to control themselves act like low-pass filters of some sort. And, you know, it may have a fairly wide bandwidth, but it's still a low-pass type filter. Because of the system having sensor noise associated with it, there may be a sensor processor that incorporates some filtering. Again, we get each of these blocks then provides a limitation or restriction on the overall bandwidth. And so it's important to understand, the author makes the point, it's important to understand what is the available bandwidth for the system. And if our system is unstable, we may need more bandwidth than we have available to us because of all the components. Also, the overall loop will change the bandwidth. So the bandwidth is an important issue that the author brings up. The author also brings up the point that controls are often operationally critical, especially for nonlinear systems, but also unstable systems. That is, if you open the loop, the system is unstable, it's going to blow up. That's not a good thing, okay? Especially if it's a nuclear reactor. So we have that. And so what happens then is we may need redundancy in our control system. So this is an illustration of redundancy for a particular aircraft. Here is for the B-2 bomber. This is a redundancy block diagram. So this shows that it uses 4 control computers. So so 4 processors. Okay, and they control the various actuators. These various processors control the various actuators, and so forth. And so it's important to have this kind of redundancy. It's also possible for there to be what are called redundant actuators. So the HRA is a device called a highly redundant actuator. So the HRA basically uses a large number of small actuators to achieve a fault-tolerant operation. Okay, so it uses a number, and so we have some in parallel, we have some in series, and so a question would be, if I have 16 actuators, is it better to put them like this that are just in 4 strands in parallel, or is it better to put them in 4 things in series like this? So that's an important question when it comes to the issue of reliability. So redundant actuators, that is, if one of these guys fails or locks up, how is that going to affect the entire operation of this thing? Okay, so suppose one of these guys locks up, how is that going to affect the entire operation of this thing? So what happens here will be very different than what happens here if one of these guys locks up. So there's also the issue of voting when it comes to fault-tolerant types of design. So here I show N sensors coming into N processors, and there'll be voting and the result coming out of that. And so a voting scheme like this can be tolerant to N, little n, simultaneous failures if capital N, the total number of redundant channels, is equal to 2n plus 1. Okay, then we can be tolerant. And so basically, this is little n simultaneous failures. And so if little n of these guys fail, and they all fail in the exact same way, then that means that leaves n plus 1 that are still functioning fine that can be used to vote out the other n. So this using a simple majority vote can be used to establish what the correct thing ought to be here. So as you can see, this whole process can get really expensive depending on how expensive all these devices are over here. And so, but it can be important if the thing absolutely, positively must survive. So the issue of control or redundancy is really the issue of fault tolerance. And in general, there are a number of issues that are associated with fault tolerance. First thing is there can be no single point of failure. Okay, so if one device goes out, that cannot cause the whole system to fail. Okay, and it doesn't matter what the part is. Okay, so single point failure is an important aspect of fault tolerance. You could also have other types of failure modes, such as 2 things failing at once, or so forth. Another important part of fault tolerance is to be able to isolate a fault of a failing component. So if we're at fault, we can isolate which component failed, and then we have what's called fault containment. That is, if a fault occurs, can we contain it? That is, can we prevent propagation of the failure? So if this one falls, we're going to have the domino effect. This one falls, which causes this one to fail, and so forth. We want to avoid that kind of fault propagation. And then the availability of reversion modes. Is it possible then, if a failure occurs, to put the system into a safe mode of some sort? Okay, that's the idea of a reversion mode. And so these are some issues associated with fault tolerance, and there's a whole field of study associated with this. In terms of redundancy, there are 3 things that are important. First is replication. That is multiple identical instances of the same subsystem that are used, and we use voting then to determine what the output will be. Replacement is associated with the idea of being able to switch to an identical replacement in the event of a failure. So let's say you've identified a fault occurs in this. Can we switch that guy out and switch in another one that works properly? And then diversity, the use of multiple different implementations. So for example, if you have replication, so you have identical subsystems that you're using. If the subsystem itself, the basic design of that subsystem has a fault in it, has a flaw in it, a bug, then all the others will have the same bug. And so that if you get into a condition where that bug becomes a problem, then your whole system fails. So that's like a single point failure. So a way to get around that is to use diversity, that is multiple different implementations, in order to provide the redundancy. And so by applying multiple different implementations, you can get some more reliability. So an example of this is a RAID array, redundant array of independent disks. So these kinds of arrays are used to make sure that data is kept secure, that you do not lose data. So if so you have an array of disks, hard disks. So if one of the disks fails, then you can recover the information and still maintain data integrity even if one of the disks fails. Okay, so RAID can also be used for doing other things. You can actually speed up performance if you have enough disks. So in other words, if you want to write to a file, instead of writing to one disk all the data, you could write to several disks parts of the data. That is, you divide up the data and write it to several disks. And so that writing process, which is generally the slow part, gets done in parallel. And so RAID can actually be used. And so there are a number of RAID modes that are used in some are for security, some are for speed, performance, those kinds of things. So redundancy is helpful. Local stability. So when we talked about the notion of stability, you can have local stability. So many linear control systems have physical limits. You can have magnitude limits, rate limits. Okay, so all kinds. You can have, for example, a saturation in the system, slew rate limitations, and so that's just a nature of the physical system. So there's no such thing as a truly linear system. And that's why I put that in quotes. There's no such thing as a truly linear system. So if you look, for example, at a resistor, V is equal to IR, that relationship rolls very well until the smoke comes out, right? Once the smoke comes out, that little thing no longer has the same resistance that it did before the smoke, while the smoke was still in, right? And so the systems are not linear. So if you exceed the power rating or the wattage, then the system will generally not behave like it did before you violated that. So system's not linear. Controllers are often designed to provide set point tracking. That's the most common type of controller that's used. And such controllers often use an integrator to provide that kind of tracking. So for example, a PID controller, proportional integral derivative. The integral is what allows the tracking to actually get to this, to keep the error between the set point and the actual output small. Okay, it's used to do that. If it starts to go away, the control signal just builds and builds until it, but that's so the integrator in a PID controller, for example, is very helpful in terms of providing zero steady state error, which is a steady state kind of property, but it's not so good in the transient response. Okay, in the transient response, it actually kind of gets in the way, and it gives rise to something called integrator windup. So basically, if you have a nonlinear system, you need to take care to avoid large control magnitudes. So in other words, you can't make your system perform too quickly or jump through the hoop too quickly, or it will have a problem. So respect the unstable. The Chernobyl nuclear reactor was a failure of the control operation. And so the whole point of this paper was to help us to be respectful of the unstable. And So even though we can stabilize an unstable system using control, which is pretty amazing, it's a pretty nice thing, the fact is we have fundamental limits, and we need to be aware of those limits, and those limits can have huge consequences. Stay tuned now for the practice problems.